Okay, so Danica is being the film director at this point and holding the camera. So here's what we're gonna do. This is kind of a culmination of a bunch of things with energy. So this is what's known as a ballistic pendulum. So I've got a little marble, and we're gonna know the mass of the marble. And I'm gonna put that in here, and then I'm gonna pull this spring back. Then I'm gonna launch it. It's gonna come in here, it's gonna hit the pendulum, and this thing is gonna swing up, and then we're gonna know the angle to which the pendulum swung up, okay? So, and then from there, we're gonna figure out a bunch of things. So, I'm gonna pull this back. Now, did I just do work? Yeah. Danica, I think you might be pointing down a little bit. Okay, so I just did work, right? Why did I do work? Force over distance. I'm compressing a spring. Can I take the force that I applied and multiply it by the distance to find the work that was done? No, you cannot do that on springs, because if you look at a force and compression graph, that's a horizontal line. With springs, you cannot take force times distance to get work. You can find the area underneath and you can go, oh, work would be 1/2 force times my elongation or my compression. That would work. That's cool, okay? You could use us equals 1/2 kx squared if you knew the spring constant. You can do that. That's cool. But what you cannot do on springs is just take force times distance, because it's more work, more force the farther you compress it. So here's what I've done. I've stored some potential energy in the spring. I've done work. Hold it back. So I'm going to put the marble in here. Then we're going to launch the marble. It's going to go flying in here. It's going to hit the pendulum, and then it's going to swing up. Okay? So 3, 2, 1. Okay? So it swung up to about 20.8 degrees. Okay? So the angle was 20.8 degrees. Okay, now, done with that. Shift that back where we can see the TV. Got it?
Yep.
Perfect. Okay. So you have to work this in sequence, okay? There's a specific sequence that you have to work this problem. So you kind of have to work backwards in the sense that here's what we're going to do. So this thing swung up to an angle of 20.8 degrees. So when it was at its highest point up here, when it was at its highest point, what's the only type of energy that it had? Potential, right? So we had UG up here. Well, the UG at the bottom had to equal the kinetic energy that it had, okay? So when you get a problem like this, and I promise you, you're going to have these energy conversion problems. I promise you. This is going to be the heart and soul of this test. Okay? So, when in doubt, and there's going to be one specific problem where I tell you, you have to draw a chart to receive full credit on the problem. So, in this situation, if you wanted to, you could sit there and go, okay, I got two types of energy. I got UG, and I've got kinetic, and then I've got the sum, okay? Now the problem is there's a whole bunch of things that we don't know. But here's the bigger idea. At the top, okay, that's going to have some amount of UG. That's going to be some number. At the top of the swing, how much kinetic energy did I have?
0.
0. Why?
Because it was all converted to potential.
Well, both of you are right. Number one, it's all potential, and it's all potential because it stopped to change direction, so my velocity is 0. So that's going to be 0. So that means the sum is going to be whatever energy that I had at the top. Now, what we're going to do is we're going to work backwards and go, well, when it was at the bottom of the swing, how much UG did I have?
0.
0. So that means that the kinetic energy that I had at the top has to be the potential energy that I had, or the kinetic energy at the bottom has to equal the potential energy at the top, which is going to be the sum value. Okay, cool. So all of these problems are going to start the same way. All of the problems are either going to be, hey, a ball was rolling, hey, a spring is compressed, or we've lifted something to the top of the hill. These are all going to start as one pure type of energy. If there's ever a calculation that you double check, it's when you find that pure form of energy. Because if that number is wrong, everything is going to be wrong. Okay? So if you ever double check a calculation, you double check that one. Okay. So, since the UG at the top, which is going to be mgh, is going to equal the kinetic energy at the bottom, that's going to be 1/2 mv squared. Okay? So what we're going to search for, because we're going to find this height. Now, to find that height, and I will give you this, if you need this equation, I will give you this equation. But that's height equals L times 1 minus cosine theta. Okay, what that allows you to do on a pendulum problem is determine the height that it has when it swings up. Okay, if you need this, I will give you this equation. Okay, don't memorize it. I will give you this equation if you need it. So in this situation, the length was, what was the length? I had it written down somewhere. 0.23 meters. So rather than do us a favor, take 0.23 meters times 1 minus the cosine of 20.8 degrees. So I take 1 minus cosine 20.8 and multiply that by 0.23.
0.015.
0.015 meters. Okay? Which isn't very high. Okay? So what we're saying is that even though this thing swung up here like this, okay, which wasn't much, but the vertical distance that it swung up was 1.5 centimeters, which is about like yay. Okay? So that's what happened. So it swung up on an arc, but that's how high it was above the ground, 1.5. Okay. So now we have our height. We know what G is. Now let's talk about mass. There's 3 potential masses that it could be. It could be the mass of the marble by itself. It could be the mass of the pendulum, or it could be the combined mass of the pendulum and the marble. Okay? So we got marble, pendulum, combined mass. So clearly, at the top of the swing, which mass is it? The combined or the pendulum or just the marble? Do not make this difficult. Where's the marble? Inside the pendulum, right? So when it swings to the top, guess what? That's the combined mass. So the mass at the top is going to be the combined mass because the marble was stuck inside the pendulum. It's like a California problem, right? So this mass up here is the total mass. So that's the total mass. So is this mass down here also the total mass? But here's what I want you to think through. If I shot that marble and it missed and it didn't hit the pendulum, would the pendulum swing up to any distance at all? No. So the only way this thing has any kinetic energy is because of the fact that that mass is the combined mass as well. So the masses are both the same. This is where this is going to get relatively easy. So the masses are the same. So if the masses are the same, what can you do with them?
Cancel them out.
Cancel them out. Oh, okay, that just goes away, right? So then I'm left with, because I hate fractions, multiply by 2. So all of this is that equation, that v squared equaling v naught squared plus 2ab. Well, on this one, all we did was say, oh, okay, right. The initial velocity at the bottom or at the top is going to be 0. That's going to drop out. So all we have left is this part of it, and I'm going to take the square root of it. So all of that equation did was just come from the idea that energy had to be conserved. So it's just that equation, okay? So, Ryan, do us a favor. Take 2 times 9.8 meters per second squared times 0.015, and then take the square root of that.
0.542.
0.542 meters per second. Okay? So that's how fast that was moving at the bottom to swing up to a height. And you're going, well, that isn't very fast. Well, it didn't swing up very far either, okay? It only swung up this far, okay? So it isn't like, whoa, it swung up to hit the ceiling, okay? It only swung up that far. So it's not going that fast.
You said how fast it was going at the bottom to reach
Yes.
the top.
Yep. Now, what we're ultimately after is the velocity of the marble. And this is when this is actually, it's called a ballistic pendulum. Because if you're trying to figure out like the speed of a rifle bullet, you can't really like shoot a bullet and go start, stop, okay? It isn't like drill running out in the hallway where we can just see the start and finish point. You can't do that with a high-speed bullet. So literally, this is what they do. They shoot it into something, and it swings up, and you work backwards, and you find the velocity of the bullet. And that's what we're trying to do. We're trying to figure out how fast was the marble going to when that thing got shot out. Okay, cool. So this is the sequence that you have to work this problem. It's like the alphabet. The first thing that you do is you work the energy side of it first, okay? You work the energy side first. You do the energy first. Then the second part is that you're going to do momentum. Okay? So it's like the alphabet. You hit E before you hit momentum. Okay? Like the alphabet. So you use the energy to figure out how fast the system was going to swing up. We got that number. Now I want to work backwards, but that's the combined mass. So this is like a California problem. So okay, we can play your game, Burkamp. So the momentum of the ball plus the momentum of the pendulum is going to equal the new momentum of the ball plus the new momentum of the pendulum. Cool. Well, what was the initial momentum of the pendulum? 0. So we don't have to worry about that, right? So this is going to be the mass of the ball times the velocity of the ball. This is a California problem. So what can we do on the momentum side?
Combine.
What did you say? You said it, Emma.
Combine them.
Yeah, or factor out that velocity, right? So this would be the mass of the pendulum plus the mass of the ball times v prime. So the 0.542 is the v prime, because that's how fast the system was moving before it moved off, right? That's how fast it was moving, because that's how high it swung up. So I'm going to divide both sides by the mass of the ball, because that's what I don't know. Now, you can do this as long as everything is in grams, and I've always preached, hey, convert it into kilograms. But in this particular problem, you can just leave everything in grams, because you're just going to multiply everything by 1,000 anyway, and you're still going to get the same answer. Shh, don't tell anybody. So, now if you're hardcore, it's like, oh, Burkamp, no, I've got to work in kilograms, fine, whatever. So you got 86.2 and 8.38. So I got 86.20 grams plus, and then we have a coefficient more, 8.38 grams times 0.542. And then I'm going to divide that by 8.38 grams. So take 86.2 plus 8.38, multiply that by 0.542, and then divide that by 8.38.
83 point. Is it 8.38? 83 point.
Divided by 8.38. So it's 86.2 plus 8.38. Get that number. Multiply that by 0.542. And then divide all of that by 8.38.
6.12.
6.12 meters per second. So that's how fast the marble was launched coming out of the spring. Now, here's what you cannot do. Okay? Here's what you cannot do. In this particular problem, because of the fact that I compressed that spring, so if you look at what I did at the beginning, I compressed the spring. So what I can't do is take the energy that I compress in the spring and say, oh, that's the energy that I'm going to have up at the top. The reason I cannot do that on this particular problem is that any time objects hit and they stick together, you lose energy, okay? So this is why I cannot do this. Now, if I just did this, if I just compressed the spring and let go of it and just launched the marble, then I could take the work that I do in compressing the spring and set that equal to the velocity of the marble. I could do that, okay? But in terms of the pendulum, I can't take the energy of the spring and set that equal to the energy at the top of the pendulum because of the fact that I lose energy in the collision process itself, okay? So you just have to be careful of that. I promise you, there's a question like this on the review. I promise you, you're gonna have a question like this on the test, okay? Promise you. Now, I gotta give you one thing right quick. Just keep the camera rolling for a second. I'll be right back.
His shoes sound like that one lamp guy when you were watching Pixar. He's like, and he jumps on the eye, you know what I'm talking about? Like this. He's like,
Okay, so this is what's known as Newton's cradle, okay? And so I'll try and put this, can they see it?
now we can. Yep.
Can you see it? Okay. So here's the story. If I lift one up, one flies out, okay? So in this situation, I'm conserving both energy and momentum because I lift one up, I do work, I store a certain amount of energy. I let go of it. That energy that I store as UG becomes kinetic energy. That translates into one flying out with the same amount. Eventually these stop because you hear it. There's vibrations, you have collisions. So you lose some energy in that process, okay? But at the beginning, I lift one up, one flies out. Now, if I lift two up, okay, there's one of two things that can happen. When I lift two up, two could come out, that's an option. Or I lift two up and one comes out going twice as fast, okay? So if I did that, if I lifted two up and they came in and one came out with going twice as fast, would I conserve momentum? If one left with twice the velocity, would that have the same momentum as two with half the velocity? Totally pause. Yes, okay? Because what would happen is that we would have, if I lifted up 2, so that would be, if you think about it, 2m times some velocity when it hit. If 1 flew out, that would be mass times 2v. So 1 mass times 2v is equal to 2m times 1v. Okay? So if that happened, momentum would be conserved. But we also have to conserve energy. Okay? So if you look at this kinetic energy when it hits would be 1/2 times 2m times v squared. Okay, that's how it would calculate the kinetic energy, right? And so the 2 would cancel out, and I would get mv squared. So the amount of kinetic energy that 2 has coming in, I could just write as mv squared. Now, if 1 takes off with twice the velocity, I can conserve momentum. That's cool. But the energy becomes kinetic energy 1/2 m times m, because it's just 1 mass, but that's flying out at 2v squared. Well, that becomes 1/2 m times 4v squared, which becomes m times 2v squared. So m times 2v squared is bigger than mv squared. So when I take 2 and I lift it up, 2 have to go flying out. I can't have 1 fly out going twice as fast because I would be creating energy. So if I take 2 go up. If I take 3 go out. Do 4, well, it works better if it's stable. Okay. If I do 5, cool. Okay. Dramatic finish when you do 5. Like, oh, what's going to happen? I don't know. Okay. So let's talk about problems that are going to be on the test. Certain problems I promise you are going to be on the test. You're going to have a problem that I promise you. You're going to have like some type of spring, some object moving like a book or something, and then it's going to go up the hill. Okay? So you're going to have a problem that's going to involve 3 things. A spring, so you're going to have us. You're going to have it moving by itself, so you're going to have kinetic energy. And then you're going to have it go up a hill, so you're going to have UG. So you're going to have KT, us, and UG. Okay? Promise you, you're going to have a problem like that. And this is the one I'm going to tell you. You have to have a chart that says, here's my us, here's my UG, here's my KT, here's the sum. This problem will involve Babar the elephant. Okay, I'm going to tell you straight up. Here's going to be the character in this. Look for Babar. When you see Babar the elephant, this is going to be the problem. Okay, Babar is going to be moving. Okay, hit a spring, go back up a hill. Okay, Babar, this is going to be the one. I promise you, you're going to have one, and this is why I gave you that assignment back, where you're going to have something that's going to roll down a hill, okay? And in this one, here's the process. You start with UG at the top, is going to equal KT plus KR, and this is the deal where you have to go 1/2 mv squared plus 1/2 I omega squared. So what do you have to do for that omega?
V squared over R squared.
Beautiful. So that I, that moment of inertia, it might be like a solid cylinder, which would be 1/2 mr squared. And then for the omega, you've got to do the v squared over r squared. That allows the r squareds to cancel out. And then you have everything in terms of v. Promise you, you're going to have a problem like that. Promise you, you're going to have a question with a satellite. where you have to make it spin, okay? I'm not gonna make you do like the orbital velocity and period and that type of thing. This is all just gonna be about making the satellite spin, okay? Ay, 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 okay? So on the problem that, this is gonna be this type of problem. The assignment that I just gave back, it was the satellite problem, okay? The only thing I'm gonna tell you straight up, it's gonna be, I'm gonna treat it as a solid cylinder. It's gonna be 1/2 mr squared from the moment of inertia. You have the problem, and there's gonna be problems like this on the review too. The only thing I can do is change the numbers, okay? That's it. That's the only thing I can do. I can change the mass of the satellite, I can change the radius of the satellite, and I can change how fast we want the satellite to spin. That's it. Everything else stays the same. On the problem like where it's gonna roll down, the only thing I can change is the type of object that's rolling. Is it a ball? Is it a hollow sphere? Is it a thin hoop? Okay? It's the process. Understand the process, and then go, oh, okay, right, this is a cylinder. I use 1/2 mr squared, okay? It's the only thing I can change. I promise you there's gonna be a ballistic pendulum problem. How do you work it first? Energy or momentum?
Energy.
Energy. Now, speaking of energy, let's say I'm gonna have 3 different situations. Let me see. Situation number 1, I'm going to have a frictionless ramp. Situation number 2, I'm just going to have something fall straight down. Situation number 3, it's going to go out like a lemming problem. Okay? So on all of these, the height is going to be the same. Okay? They're all going to have the same initial height. Okay? Straight across. They're all going to have the same initial height. Since they all have the same initial height and the mass is going to be the same, what else are they all going to have in common?
Same potential energy.
They're all going to have the same UG. Okay? They're all going to have the same UG because they're all going to be at the same height. They're all going to have the same UG. What's the only difference between that one on the end versus the other 2?
It's getting higher.
Well, what type of energy does this one have that the other 2 don't? Yeah, these I'm just going to let go. These are just going to slide down. So this object, boom, I'm going to let go. It's just going to slide down. This one, I'm going to let go. It's going to fall straight down. This one is going to go out. So this is the only one that has UG and KT. Because the other ones don't have kinetic energy, they just have UG. So if that's the situation, which one starts with the most energy?
No.
That one.
Then
The end one. That one. The end. Right? That one starts with the most energy. So which one is going to land with the most energy? That one. Okay. Just keep that in mind. Which of the 3 will take the longest to hit the ground? The ramp, straight down, or the one that gets shot out, or would they all be the same amount of time?
same.
Same amount of time.
Ramp. No.
Everybody cool with it's going to be the same amount of time? Like that? They're all going to hit at the same time.
I feel like it's the ramp.
Huh?
I feel like it's the ramp.
That's going to take,
The longest.
you're right.
Because it's a further distance.
Okay, number 1, it's got to slide down the ramp. Okay? If it's sliding down the ramp, think about this one. what's gonna be the acceleration of the one that falls straight down?
9.8
9.8.
meters.
What's gonna be the acceleration of the one that gets shot out as a lemming? 9.8. This is on a ramp. What does the acceleration have to be less than?
9.8.
So this one's gonna have the smallest acceleration because of the fact that it's only the force parallel that's making it move down the ramp. Okay? Tell me, Pauls.
The one in the middle you said doesn't have kinetic energy, but I thought whenever it was like falling, they like.
No, it doesn't have initial kinetic energy.
Oh, okay.
Because I'm just gonna drop it like this. Okay? So this one, the one in the middle, I just dropped. The one on the end, I throw like that.
So it still has it. It just
The ramp
doesn't
is
start
the
with
slopes.
it.
Yeah, it'll have it once it starts to move.
Okay.
But I'm just saying, I'm not throwing it down.
Okay.
I'm just dropping it.
Okay.
Okay? Got that. Okay, so when you get the review, there's gonna be some questions on there that you're gonna read it and go, oh my God, we haven't covered this. You're right. Because normally I have a day to spend on buoyancy. I didn't have time to do that. There's also gonna be some questions on there that will talk about elastic collisions. I didn't have time to cover elastic collisions anyway. So if you see a question and it's like, oh my God, we've never talked about this. Don't worry about the questions, only some of them on there. So if you see something about buoyancy, don't worry about it. It's not gonna be on the test. So if you read a question and you go, I swear to God, we never did this, it's not gonna be on the test, okay? But to give you some idea of, so here's what's gonna happen. You're gonna have, okay, so let me explain what you're gonna get. So there's actually like 3 parts to the review because this is the unit that always gets twerked at the end because sometimes I have more days, sometimes I have longer days. So this is why I like have all of these 3 different reviews. And so I just ran them off for, that way you have all 3. So, like on this one, you have number 4. This is the one where the bullet hits the pendulum and it swings up. So this is like the ballistic pendulum problem, okay? And then this one where you've got kind of a spring and this combines a spring with a lemming problem. Oh, okay, I have kinetic energy up here. It's going to hit this and they're going to go flying off. So this is like a spring meets a lemming problem. So you can get that and the answer key to that. This one, the review, this one has 6 problems. Like this one, number 6, this is the one where you take a pendulum and you lift it up and you let it fall. It has the satellite problem on it. It has the hollow sphere that's going to roll down the ramp. So this is kind of the heart and soul of this. And then you're going to get the answer key to that, okay? Now, on this one, the rock and review of mechanical and thermal energy, this one has, like on number 8, it has a question about the buoyancy force. Don't worry about number 8. It's not going to be on the test, okay? Because we didn't cover buoyancy. Don't worry about it. It's not going to be there. But it has one like a number 9, like how much energy does it take 0.1 kilogram of ice at minus 10 to water at 80 degrees Celsius? That one you do have to have. And so what's going to happen tomorrow, you're going to have your normal equation sheets. You're also going to have that sheet that has all of those constants on it, like thermal expansion, the specific heats. Don't memorize like, oh man, I got to memorize all the specific heat values. No, okay? I'm a jerk. I'm not that big of a jerk that I'm going to make you memorize a sheet of random constants that you're just going to forget on the test anyway. So like here on number 7, this is this big question with an ideal gas. So number 7 starts at A and goes all the way through O, okay? So literally it goes A through O. It's the longest problem I've ever written. So anyway, so those sheets are over here. So, yeah, those 2 are together. So these are the ones that are together, and then you've got those, and then you've got, okay. So we put them together.
Like I would use sheet off that energy.
Yeah.
I bet you can. I know.
What was it? Yeah, too stupid.
Okay, so let's go with that. That goes with that. Okay, there you go. You're off to the races. You're on your own.